I will share the first session of the morning. I have the pleasure to introduce Dr. Vincent Tournat, Professor Vincent Tournat, Prof. Vincent Tournat is a French scientist from a laboratory well known in acoustic in France and in Europe. It is a lone laboratory of acoustic in Le Mans. Le Mans is known for another type of race car, but there are also a lot of very nice acousticians. So Vincent Tournat will present us some results in acoustic nonlinear waves in flexible mechanical metamaterials. So coupling metamaterials and acoustic. It is now your presentation and you can begin now. Thank you very much.
Thank you, Yves. Thank you for the invitation to give this talk. So, as I said, I'm Vincent Tournat, and this work that we'll be presenting is a collaborative work with two groups: the group of Katia Bertoldi at Harvard and the group of Georgian Rani at UPenn. So, the materials, the systems that we are dealing with and in which we study wave propagation are this type of systems that are very flexible. We look at mechanical waves in there, so there won't be any sound really, but waves propagating in there. And they can be fabricated in very different ways. This is an example of a rubber plate which is laser cut that can be made monostable or bistable. So we study waves in there, large deformations. There are also examples of these systems that have been studied for their static properties, but also for mitigating impacts that are 3D printed with PDMS polymer, soft polymer directly, and that can be made bistable just by the geometry of their structure. And we don't see well here, but they can be used to absorb impacts. And finally, let me show you a last example of systems that we've been studying, where the different elements of the medium can be assembled, and most of the time we assemble rigid elements, rigid masses with various shapes like this one here, and we connect them with flexible films. Thin films that can be highly deformed and that play the role of the elastic restoring force in there. And recently we've been looking at new ways of fabricating them, coupling 3D printing of plastic and assembling with this flexible ships. So all these materials, they share some sort of common points. We are interested in them because they have very flexible elements. So here, that would be in a porous structure with holes. It would be the thin ligaments connecting the more bulky parts. Origami can be seen also. Origamis can be seen as flexible elastic metamaterials or mechanical metamaterials because at the folds you have a flexible part and the plates are more rigid. And finally, other types of mechanical structures. So what is interesting for us, we are not specialists of homogenization, and it would require to do it in the dynamic regime, nonlinear regime, large deformations. So what is interesting for us is that from these types of models with rigid masses and connected between them with flexible elements, we can use lumped parameters model and write down the motion equations and deal with that. So this is what is interesting for us, to be able to model these, and I will talk about that a bit later. So all these structures that we've been studying have the same common features of soft elastic elements coupling more rigid ones. And so we started, and we were inspired by this type of work some years ago, looking at these systems that can be seen as, have been studied a lot in statics, but that can be seen as a rubber plate with holes, or you can see also this differently as a rotating square structure. We call it rotating square structure because when you deform it strongly, you also see squares that are rotating and that are connected with thinner ligaments between them. And so what triggered interest for us is that in this system you have obviously some nonlinear stress-strain relationships that show buckling, but also sometimes just nonlinearity, more classical nonlinearity. And it comes from a geometrical source of nonlinearity, which is interesting for us because in acoustics or for waves, we've been mostly dealing with nonlinearity, but not being able to harness it or design it from the structure. And we thought, oh, maybe we can use geometrical parameters of the structure, elastic parameters of the structures to design the nonlinearity we want for the waves. And so first we asked these questions: can we study, can we look, can we observe nonlinear waves in these systems? And then can we control them by changing some of the parameters rationally in the structure? So yeah, I will divide my talk in two main parts. The first part is mostly about the methodology and some examples of early work that we've been doing, and I will, in the second part, go to some more recent results of this year. So historically, for looking at these waves, we started with such samples that were printed in a lab at Harvard, where they would use PGMs and print the shapes they wanted. And we started with this rotating square structure, or this like square holes rubber plate structure. And we experimentally tried to observe waves. So we would punch on one side of the sample. It's not very thick, so you can already feel that there could be like problems with that. And one of the first problems we faced, it's probably obvious now, but is that the plate would buckle out of plane. And so we had to deal with that. We ended up using an elongated sample, which is suitable for looking at the waves propagating in there, with initially rotated squares, which softens effectively the structure. And we also included some large masses in there in order to make the pulses that we propagating in there a bit narrower and slower, so that we could observe them. So this is the type of sample we've been looking at. And the typical experiments, I start with the experiments here, is this one. We have an impactor here that we derive with an impact. So it can be either a manual impact with a hammer or a more controlled one. And what you maybe see here is a pulse propagating along the sample. The video is repeated. It's not a very fast process, actually. We can use 1,000 frames per second, so it's something that you can almost see, actually. You can see the movements. But to study it, we use that, and we use the digital image correlation to characterize these pulses. So yeah, there are a few subtleties about that, but we can control more or less the impact we make by changing the initial gap in the holder that we have, or by changing also the force that we put in the impact. So these are examples of induced impact. These are the displacements of the first unit on the left, close to the impactor, as a function of time. And you see we can reach different rising rates or amplitudes with different impacts. And we decided to characterize these impacts with only two parameters: the initial velocity and the max displacement that were induced by the impacts. So we would not control the impacts beforehand, but we will like treat the movie and see what did we input in there, trying to vary these things. And this is a typical example of an experimental result. So you have time and space here, the number of units along the sample. And what you see is some front propagating, so you have a wave propagating in there. when we look at different snapshots of the displacements as a function of space, and for 4 different times in the system, we see these fronts propagating. And what was surprising for us, because it's a periodic system, discrete, is that these fronts are rather stable along propagation. They look the same along propagation, which was quite surprising. We would expect, for instance, frequency band gaps, a strong dispersion, and because they are not very long wavelengths sometimes, we were a bit surprised. So we decided to look and to dig into that. And so this is where I just maybe describe a bit how we model this as an example, and we've been using this type of modeling, sometimes a bit different, for many systems we've been studying later. So most of the deformation occurs at the joints, thin ligaments. This is kind of obvious in the system, and in the quasi-static case it's like that, and in the dynamic case there is no reason it's not similar for these frequencies that we have. So we decided to use this lump parameter modeling, where we consider, for instance, a mass, a rigid mass here, a square, connected to the 4 neighbors. And we suppose it's rigid. It has 2 degrees of freedom in this case, because we induce plane waves. So one displacement and 1 rotation for each mass. And then we couple this mass with effective springs that can be longitudinal, shear, or bending springs that we have to find out. And so we end up with a system of 2 equations of motion for each particle. So for a finite sample of like hundreds of particles, it's 200 equations of motion, and for the 2 degrees of freedom. And we just to show you these, we derive them by hand. It's not that hard. With the normalizations of this type, we have second order derivatives in time of the displacement, second order derivative in time of the rotation for each unit, and equal some terms. And okay, we can have a look to these equations a bit more in detail, but we have parts that are very similar to chains of masses and springs, chains of resonators coupled, and at the end we have a number of terms containing cosine functions due to the rotation of the particles that couple the 2 equations and provide nonlinearity. So to deal with that, we simplify things at some point. So as I repeated, we are not doing homogenization in there. It's a very, let's say, wave approach that we use most of the time for these discrete systems. We go to the continuum approximation for the space. We take the first order nonlinear terms of the sine and cosine functions. So we limit ourselves to finite amplitude, but small ones. And we end up with 2 partial differential equations for the whole system. Once again, one in displacement and one in rotation with coupled terms, coupling terms. And then the trick we use is to look for propagating wave solutions. So we take this traveling frame of coordinate, and we substitute that. We go to these 2 equations again with we can identify terms, and we can deal actually with that to end up with a single equation for the system and a coupling one, a single equation for the rotational degree of freedom. And this single equation is actually fully integrable. It's a nonlinear Klein-Gordon equation with the propagating operator, the dispersion, and the nonlinearity, and there are analytical solutions of this. And analytical solutions exist in the form of solitons. So I don't know if all of you are familiar with solitons, but I will say a few words about that. So let's say the beauty for us is that we have an equation with parameters P and Q that depend on geometrical parameters of our structure, elastic parameters of our structure, inertial parameters. So things that we can rationally vary, change when we fabricate the samples to influence these 2 terms actually, and the propagation. So we can tune the nonlinearity and the dispersion of the waves. And the solution that we are interested in, the pulse solution, looks like this. It's the analytical solution of the Klein-Gordon, this Klein-Gordon equation, and we have a hyperbolic secant square function that travels with the traveling wave coordinate here. It's a vector soliton, vector because there are two components, a displacement and a rotation, that are coupled. So it's a vectorial field, let's say, in this system. And it's a very stable solution, although we are in a nonlinear and dispersive system. So these solitons, maybe I can say a few words about that, but they occur in systems with dispersion and nonlinearity. Dispersion, the velocity depends on frequency, so if you send a pulse, you will have some dispersion of the wave in, going to this type of signals. In a nonlinear system, you can go to shock waves or harmonic generation, for instance. So you would change the profile of the wave. The wave velocity depends on the amplitude. And solitons occur in these systems with nonlinearity and dispersion when these two effects balance each other perfectly, leading to waves that are nonlinear, dispersive, in a dispersive system, but that have a stable shape along propagation, and yeah, they are a stable solution. They are interesting because then there is no distortion along propagation. And historically, it was first observed for water waves, shallow water waves, by Russell, and later described in the 50s, 60s for many systems like optics and so on. And one of the defining properties of solitons is that they can cross each other like classical particles. They maybe interact at the point they cross, but then they emerge unchanged from the collision process. So this is a very interesting thing for nonlinear waves that sort of defines also solitons. Anyway, we have solitons solutions in this system, and we can go back to the full system of equations of motion with full nonlinearity, discreteness, and so on, solve this numerically, and compare with the analytical solution for the same parameters, of course. And we see a good agreement between the theoretical solution, analytical solution, and the full discrete model. Fine, so this is what we have right now. Just to mention it, for solitons, there is a unique constraints, a unique set of parameters that couple the width of the soliton, of the hyperbolic secant function, the amplitude and the speed of the soliton. So you can have an infinite number of solutions, but they should like, fulfill the constraints that come from this analytical solution. Anyway, we can now compare our full numerical model and the experiments, and we saw also good agreement, showing that we have agreement between theoretical analytical solution that we cannot plot for any sort of signals, but between the full model and the experiment, we have this agreement. So here I plot, as a function of space, I plot the displacement signal of the units for different impacts of different amplitudes in initial velocity. We record the first impact, the experimental first impact, and we feed the numerical model with that to see how it evolves along propagation. And at some time in along propagation, we compare the full numerical solution with the experimental one, and this is what you have here. The lines compared to the symbols are the numerical solutions compared to the experiments, and we see rather good agreement, at least qualitative here. The same can be done with a single experiment, looking at different times, and we see that this evolution also is recovered. So this is the methodology we used, and this is one of the first work we've done on these systems. And so we could predict vector solitons, so interesting nonlinear objects for waves in these systems. And we could show that by tuning some parameters rationally in the structure, we could also affect the velocity, the amplitude, the types of solution we have. So from there, we went to other problems a bit more advanced, let's say, than a single strip of propagation medium. We went to 2D, for instance, with these systems. So if you can print quasi 2D, you can print fully 2D. And this is the same system, but printed in a circle. And experiments look like that. So here it's DIC processing, digital image correlation processing of the experiment. And we impacted the samples the sample at different places. Here at, let's say, 0 degree compared to the horizontal line, looking at the propagation along the horizontal line of the sample, and then progressively exciting at different points in the system, looking at propagation along like 45 degrees here. And so, okay, we got this result. Actually, the analytical modeling is also doable in 2D. So that's what we've done. We could predict things like 2 modes of solitons in there and so on. I won't go into these details, but just to show the qualitative agreement between the numerical simulations of the full equations of motion and the experiments, we could see similar things, actually. So when you look at these pulses here, they share the same features. And one of the interesting features here at 45 degrees that we could highlight is the fact that there is no also diffraction of the pulse that we emit. It's a sort of sound bullet that was observed earlier in optics. It's a spatio-temporal soliton. Both the dimension along propagation and the dimension across propagation don't evolve along propagation. So it's really a pulse of energy localized in space that propagates without changing shape in this case. Well, just to wrap up this first part and go to the more recent results, I want to say that so we've been studying at the moment only rotating square structures, periodic structures. We use the periodicity as an ingredient to solve the problem. We can tune the parameters of the system to get to different equations, different nonlinearity, and everything in between. So we can play with all these. And we studied systems or waves that were also propagating along the surface waves that we could also show, or waves in systems where you induce static deformation and changes of like the geometrical and stress parameters in the system to guide, for instance, the waves. If you're interested into that, we've wrapped up some of our results and of the results of this small community working on these wave effects, nonlinear wave effects in these systems, in a 2021 review article where you can see people looked at diode effect, so systems that allow propagation in one direction of the sample but not in the other, for instance. Looking at anomalous collisions between these solitons, impact mitigation with Kressling origami structures, for instance, that are also part of this family. And I won't talk about that today, but I'm very interested these days in waves in systems that are multi-stable, that can be in 2 stable states, for instance, or more, and that can support also transition waves that are waves changing the state of the system from one to another while they are propagating. And this is a whole different world and story because the tools are very different to solve these problems, but they are very interesting because then you can also see interactions between solitons, these waves, and use waves to reconfigure systems and so on. But I won't talk about that. I would like to wrap up this talk with more recent work that we've been doing this year with the group of Katia Bertoli at Harvard, and the main player that I have to acknowledge here is Giovanni Bordiga, who is a postdoc there. And so what we've done in this context is to go beyond the periodic systems. So we still deal and speak about the same systems, rigid particles in blue connected with neighbors with very flexible elements, and you'll see that they are very similar to what we've been looking at before. But here what we use to optimize these systems or to deal with these systems is a computer approach, where we compute the whole Lagrangian energies in the system, depending on every single position of every single vertices of the blocks. So typically we would take this type of systems, 16 by 24 particles with 3 degrees of freedom. They can move in one direction, in the other direction, and they can rotate. Very connected with the micropolar and Kossler elasticity, probably. I'm not a specialist of that. And then you can imagine the number of degrees of freedom for the design parameters. Every single corner of these masses can be moving in space with some constraints, because you don't want the particles to overlap too much or to be with very weird shapes or something. But so we impose constraints on the design, but there is a lot of degrees of freedom in there. So the Lagrangians of these discrete Lagrangians of these systems are computed numerically. We can calculate them, and we make use at the end of all the parameters of the system, geometric parameters, the bond parameters, the coupling, the particles, damping, loading, etc. parameters, and initial conditions maybe, to solve the forward problem, integrating these motion equations that we have with the Lagrangian. And we make use of tools that have been developed recently for machine learning, deep learning, which some of you might know much better than me, which allow automatic differentiation of the functions that we have. So we have a forward problem of wave propagation in there, dynamic problem, time in the time domain, and we can differentiate the result regarding any of the parameters of the system. So any position of a single vertices, if we move it one way, how will it affect the final result? We know that thanks to automatic differentiation. And the forward simulation of this system, as we would do it before with MATLAB or something, would take maybe only 1 minute or 2 minutes. But the beauty of this thing is that it takes probably only a fraction of a second, so we can optimize it also, knowing all the gradients and some cost function, we can optimize this system. Fine, so what to choose to optimize? So we have a 16 by 24 problem. So one of the first things we thought about is, okay, let's say we have an input here, region where we drive 2 units of the system, and we drive them with this signal, a pulse. Okay, let's see what happens in there. And in this region, these 4 units, we decided to maximize the kinetic energy. We want to focus energy there. Let's say you can think of maybe energy harvesting or things like that, but we are not there yet for us at least. Then we have also boundary conditions here. We fix the sample. This is just because we always think about experiments, so this was more handy for doing experiments. And so we have a cost function. We want to maximize this kinetic energy, which is, as you see, the sum of the kinetic energies related to the 3 degrees of freedom of the particles. Fine. So this is the optimization process. It goes rather fast. Probably the optimization takes some minutes, 5 minutes over the whole, like for 60 iterations roughly. And it goes like this. So over time, our number of iterations, you can see here the focused energy, which is increasing, and the design that changes to something that was probably hard to imagine before. Okay, you can maybe anticipate that to maximize the kinetic energy, you need big masses. This is one thing, but it's hard to say more what happens around or along the propagation of in the first unit of the system. Well, we go to that, and so what we did is to fabricate this sample, actually, corresponding to this optimized configuration, and do experiments. So just one word about experiments. So we use a shaker, very simple shaker that we couple to the two units we were driving in the numerical simulation. This sample is actually, so this one was laser cut, and then we would insert, Giovanni was inserting every single shims in some slots that we were designed in the masses and so on. Now we are 3D printed the masses and stopping the 3D printer in the middle of the printing, inserting the shims and finishing the printing. So it's more versatile, it requires less like hand work, but it's also very long actually, because there are troubles all the time. Anyway, these are the pulses we were able to excite, so it's not exactly the one for which the system was optimized. Nothing is perfect in real experimental life, but we have some pulses that we can tune with amplitude, frequency, and so on. Just show the qualitative movie of the experiments on the left and the simulations that is reproduced on the right. So it should run now. So we have a pulse. Okay, it's almost synchronized, and you see the behavior. There is nothing very smart to say about that. It moves a lot here, so we can anticipate that kinetic energy is high here. But if we treat the experimental movie by tracking, for instance, the kinetic energy, the maximum kinetic energy along a line here of particles, we see that the max kinetic energy as a function of the space here is maximum for the two units that are big here. Not only because of the mass, it's also because they move much more than the others, of course. So we have real focusing of kinetic energy in the system. Okay, so we played a bit because now that we have a tool that seems to work and can be verified experimentally, we wanted to tackle other problems than just simple focusing or simple focusing in this complex system. What about focusing, but when you are able to excite, or you excite at different places, so multi-input excitation. So the cost function is then a mix of the three forward problems here. So if you don't optimize and you take the previous sample optimized only for one input, what you have is these green dots here. The energy focused is large for the right input, but very low for the other inputs. And the optimized sample for this multi-input constraint gives something in between. And it looks like this. So this is just the simulation movie here. If it starts, I don't know if it starts. Okay, maybe not. Let's see. Oh, this one doesn't work. Okay, it doesn't work, but it shows practically the same. You have a focusing from each input. Another problem we wanted to look at also is the energy focusing in two different spots in the system, depending on the applied static pressure, because you can change the structure behavior obviously by deforming it statically. And with a static strain of 2%, we can target this region for focusing when excited here also. And for deformation of 5%, the target switches to the other one. So we switch focusing targets. Hopefully the video will work. Oh no, what? Not this one? Maybe. Okay, I should have checked that. Anyway, you see the sample compressed and the switch of the two focusing points. Finally, and I hope it will work, this one, we can also switch from one function to another. So here, in this example, for one static strain, we maximize the energy that is focused here. And for another 8% static strain, we minimize it. So let me check if it works. Oh yes, this one works, okay. So here we maximize the energy, 1% strain. And here, 8% strain, we minimize it. It doesn't move much. And you can see here what happens, which was maybe this one we could anticipate it. The system is sort of jammed in a nice way, such that contacts that are included in the simulation also play a role in this case. But it's hard to get the structure. Maybe you can get a simple structure doing that, and you with your mind. But here it's done computationally. Okay, so this is the plot showing that in one case the focused energy, or this is the peak velocity, sorry, is similar quantities. Is maximized in the region of interest for 1% strain and is minimized here for 8%. Okay, so this is what we've done recently, and to conclude my talk, I would maybe repeat that we have here a platform that is interesting for waves because we can design and control nonlinearity, control waves. And this is what is exciting to me, because we have in mind many other wave phenomena to study in there, such as all these different types of waves, pulses, wave packets, bright solitons that are also that would benefit from being able to control the medium where they propagate. And of course applications to that. And I would like to thank also the students and the colleagues I have interacted with on some of the topics that I presented, but also mostly others connected to that, from the group of Katia Bertoldi, Harvard, and our acoustic laboratory in Le Mans. Thank you.